Okay, so I wanted to do some more physics and math-based videos in addition to the electronic stuff I was doing with the Arduino. So just to sort of get started, I thought I would just go through a derivation that I know pretty well and that I think is going to be useful for, say, someone who's in thermodynamics. So one thing that we have in thermodynamics is the idea of melting. So I know this sounds like, oh yeah, we all know what melting is, but it can be a little bit more complicated. One way that I usually like to think about it is that, say we have, let's just go with a metal solid, and say these are the atoms in your metallic solid, and they are connected by springs. And these springs are bouncing back and forth. So this atom goes that way a little bit, then it goes back this way a little bit, and same with this one. Everything that's around has vibrations, right? So it's all moving all the time. And then once you have, say, this distance, if we are, it's not deep enough. So if we define it by how dense these atoms are from each other, by, say, a lattice constant A, and lattice constant B, the tetragonal system there, if this is leading to a significant amount of A, then this concept of A is a little bit too fuzzy to call it a solid anymore. So that means that it's melted. And for this, down by Lindemann, and we originally named the Lindemann criterion melting. Lindemann criterion. I know it's very original, also happens to be incredibly easy to remember. So the Lindemann criterion for melting just says that if delta R is greater than some constant, we can just call it C of R times R, then that means that we don't have a solid anymore. So it's a little bit easier to write it in this fractional form. So if we have, and let's just go ahead and take the root mean squared of that to be a little bit more exact. And if that's greater than some constant, usually about 0.1, then we don't have a solid anymore. So there you go. That's our mathematical definition of melting.